This one.
This one? Why not this one? Or this one?
They say give ammonium ion.
Ammonium ion, right? So it must be this. Correct? So now you know that it is this equation, NO3 minus plus 10H plus 8 electron, right? Now what is important is the number of electrons, because it's a redox reaction. And next, metanoate. So how do you draw the structure of metanoate? So this question actually tells you on redox as well as structure drawing. So metanoate is, how does it look like? What's the formula?
Not sure.
Okay, remember, this is your metanoic acid, correct? So metanoate is just a structure without the H. So this is your metanoate, right? So now, since this is a redox, we must find oxygen states of this metanoate. So how do you find oxygen states of the atoms here? In particular, the carbon over here, because it will be the carbon atom that will be changing its oxygen state during this redox reaction, correct? So what is the oxygen state of this carbon? How do you calculate it?
The difference in electronegativity.
So how? So if let's say I give you this molecule, carbon dioxide, how do you find out the oxygen state of oxygen and carbon?
Oxygen is -2, right?
Yeah, -2, so this is -2, so carbon is +4. So for this case, how do you calculate? It is like this, right? So how do you obtain the oxygen state of this carbon?
This oxygen is -2.
This? -2, correct. Then this one? -1? -2?
-1.
-1, okay. Then this hydrogen?
-1.
Hydrogen is -1, and this carbon is +4, is it? Well, let me teach you a very, very simple method. I call it the plus minus method. Okay? So in order to use the plus minus method, you have to understand electronegativity. How's the trend like? Right? So for example, there is an electronegativity table here. Right? You don't have to know the exact value, you just have to know the relative value. Which one is higher, which one is smaller. Right? In fact, for the minus plus method, okay, is further explained here, right? So this is the electronegativity table. So how do you use it? Well, if let's say I have carbon bonded to 4x, right, which are the same, the first question I ask myself is, for this CX bond, right, which one is more electronegative? If let's say X is an electronegative atom, what I will do is that for this bond, I put a minus plus, because this will attract electrons more towards itself, so it's minus plus. Same thing for the rest, plus minus plus minus minus plus, right? Afterwards, I just have to count the number of charges around carbon. I just add them up, I will obtain its oxygen state, which is +4. Very simple, right? Same thing for this carbon dioxide. If I have carbon, oxygen is more electronegative. So if there is 2 bonds, I'll put a 2 minus. Here it will be 2 plus, 2 plus, 2 minus. Same thing. I'll obtain it easily. Right? Now for this case, same thing. So what if there's a minus sign? It doesn't really affect this bond. This bond, electronegativity difference is still that the minus will be here, the plus will be here. Same thing for this, plus, plus, minus, minus. Oh, what about this bond? Which one is more electronegative, C or H?
C.
C, right? So it will be plus, minus plus H. Same thing, I count the sum. So for this, the sum is
Plus 2.
plus 2. So now the oxygen state of carbon is plus 2. Right? Same thing for this oxygen, it will be minus 2 because there's 2 around it. For this hydrogen is plus 1. Then what about this oxygen with a negative charge? What is its oxygen state?
Negative 2.
You sure negative 2?
Mm,
What's the rule that you learn in chapter 1, atoms, molecules and stoichiometry? The net oxygen state must add up to minus 1.
Oh,
Correct? Huh? That's the basic rule, correct? So what's the oxygen state of oxygen? This plus this plus this plus this must be negative 1, correct? So that means its oxygen state must be minus 1. Same thing if you want to calculate this way, right? So it will be minus 1, right?
Okay.
So now this is testing you on 3 things already, redox, structure, as well as see whether you can obtain the oxygen state, right? So now this is the key part. Take note is plus 2. Now let's go back to just now the equation. NO3 minus is reduced, correct? And in order to reduce it, it needs 8 electrons. So if let's say it's you react with this in 1:4 ratio, so what can you say? Each metanoate must see 1:4 ratio, that means one of these will react with 4. In other words, these 8 electrons must come from these 4 metanoate. Correct? So each metanoate will give out how many? 2. Correct? Makes sense, right? Which means that its original oxygen state of carbon should be
Plus 4.
plus 4 or 0?
Or
Plus 4 or 0? Which one?
0.
So if I have 0, that means after I give out 2, I'll be plus 2. Is it?
I'm not sure.
You're lost?
Yeah.
See, so for sodium nitrate, NO3 minus 2 metanoate HCOO minus, the ratio is 1:4. Correct? So now the number of these, so the number of electrons from HCOO, this thing must be 8 electrons, right? So that means number of electrons per HCOO minus must be 8/4, which is 2 electrons, right? So that means HCOO minus must gain 2 electrons to get back the original thing, correct? I write like that, NO3 minus plus something, something, then you get NH4 plus HCOO minus, correct? These to these, you need how many electrons?
8.
8 electrons, correct? So this to this must be 8 as well, right? Which means that since the ratio is 1:4, that means originally from here to here it must be 2, correct? Because you have to divide by 4, correct? So originally here, this oxygen state is plus 2, we already obtained just now. Plus 2, right? Did I calculate wrong? Yeah, correct. Plus 2. So it means originally it should be
It should be
think of it, okay? This is being reduced or oxidized. Is this species being reduced or oxidized? It's being reduced, correct? Reduced, so from here to here is reduced. So from here to here it must be oxidized. Oxidized, in other words, like that. So which one will have a higher oxygen state? This one or this one? It will be this one. So that means this must be a lower number, right? It must be 0, in other words. Correct? Does it make sense?
Yeah.
Makes sense, right? So now you have to work out which one of these has oxygen state of 0. Right? So for example, the first one, OCCO, how do you work this out? What's the oxygen state of oxygen?
-2.
Okay, then carbon,
+4.
you sure?
+2.
Then the other carbon is +2 and the last one is 0. Sorry, -2, correct? So +2 to +2, it cannot be A. Because A means no change. Right, what about B? Nitrogen is -3, right? While carbon must be +3, because the other carbon is 0, right? So for the other carbon, it's what?
Carbon.
Remember, it's like that. H, H, H. Same thing, minus plus method. Carbon is more electronegative. So there's a net of -3, because this carbon is 0. So it can't be -3, because you will become an oxidate. It doesn't fit the number of electrons. So what about next one, C?
This one is this carbon is +1, and this one is
-3. Okay, then the last one.
+4.
So +4. Okay. So I said this question wrong. Is it 1 to 4 or 4 is to 1? There's a mistake somewhere. But never mind. Because eventually you should have a product with oxygen state of 0, carbon with oxygen state of 0, right? So you should have a species with carbon of oxygen state of 0. Maybe one of the options I accidentally put a H somewhere, right? But never mind. You understand how to handle these kind of questions now, right? And let me see. You will see a similar question like this somewhere, right? I'll show you next time. So let's move on to this first. So do you have a problem with this?
Yeah, this one, like, the X can be
Anything, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can it be 1000?
No.
What's the highest number X can be?
10, right?
10, right? Why? Why 10?
Like, then it will be alkane, then it will be saturated already.
Yes, correct. So maximum can be 10, right? So how many possibilities are there? What are the possibilities that you managed to get? Do you draw it?
Only like this one.
Only two? It can be C4H10, right? Can it be C4H9?
It can.
Can or cannot? C4H9. Why can?
I don't know, because maybe you can take out one H.
Now if let's say you have a formula C, let's say you have a formula, right? C2H3. Is it possible? Is C2H3 possible?
No.
No, it's not possible. Why? Because if let's say there are no other elements present, it can only be even numbers. C2H4, C2H2, C2H6, right? Why can't you have odd number? Now if let's say you have this 1, 2, 3, 4, C4H10, correct? If let's say you form a double bond, you have the formula of C4H8, correct? If let's say you form a ring, you have a formula of C4H8 as well. You cannot have C4H9. It's not possible. Alright? Now if let's say you form two double bonds, one here, your formula will become C4H6. Of course can you have two rings? You can have two rings, right? Nobody say you can't, right? 1, 2, 3, 4, I never break the octet rule, so it's possible. So what is the formula? C4H 1, 2, 3, 4, 5, 6. C4H6. You can never have a odd number, because whenever you decrease the number of hydrogen, it's always by 2, right? So you can forget about all the odd numbers. So what you will do is that you will start off with C4H10, because that's the maximum. See how many you can write out. C4H8, C4H6, C4H4, and maybe C4H2, right? So C4H10 is the easiest. You really even need two. One of which is this, the other one is this. Correct? What about C4H8? It's an alkene, correct? One double bond, so a double bond can be here or here. You sure can be alkene? What does it say here?
Alkene.
Alkane, take note, this is a trick question. So you cannot have any double bonds, but you can have rings. Nobody say you can't. If you have a cyclic ring, it's also known as an alkane, correct? It's a cycloalkane. So this is your C4H8. Are there any more formulas with? Are there any more structures with this formula? You have a 4-member ring, correct? Why not shift down to a 3-member ring? This is also C4H8, right? Do you go through the degree of unsaturation, degree of saturation thing? Not yet, huh? So maybe I'll go through it later, right? So this is the degree of, later on I'll teach you, right? It's in my isomerism notes, right? So C4H8, you can have this, whereby you have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, correct? So can you have any other pattern for C4H8? You can't. Basically, these can only attach here, 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 which is the same. You can't have a 2-member ring, right? Next is C4H6. Same thing, since you cannot have double bonds, you must move on to ring systems, right? So for C4H6, you need to have 2 rings. So one of which is the one which I drew just now. Okay.
How do you form these 2 rings?
So this is here, carbon, carbon, hydrogen, 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 hydrogen. Correct. None of which breaks the octet rule. Correct. So it's possible, right? Although it is unstable, but it's possible, right? I'm not asking for which one is stable, right? So this is C4H6. Are there any more structures with 2 rings? Looks like this is the only possibility, correct? If you are thinking about this is the same as this, correct? If you turn it this way is the same. Are there any more? No more, right? What about C4H4? Means we have how many rings? For these you have 0 rings, by the way. These you have 1 ring. These you have 2 rings. So for these you should have 3 rings. So can you form a structure with this formula and with 3 rings?
It's impossible, right?
Is it possible? I never break any octet rule, right? Hydrogen, 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 hydrogen. That's nice. Why? That's why you must think out of the box, right? That's the purpose of me setting this question. Because a lot of students will forget about this. And I also never say cannot. I just say C4H(X). Correct? So this is testing the student where they can think out of the box. This is of course an alkane, correct? For this kind of alkane is known as a platonic alkane. Of course there can be other forms of platonic alkane, one of which is this question. This is also another form. Right? I thought after you do until here you should have some idea to do this question, right? So this is the last form, and of course you cannot have C4H2. It's not possible to have 5 rings. 4 rings. This is the maximum already. Right? So in total you have 1, 2, 3, 4, 5, 6. Right? So next, question 3. There's a typo here. It should be can, not cannot. Right? I think in the original one it says cannot. So what do you choose? B. And then I will go through these together, right? So these kind of questions, it might seem very hard. And in fact, I can tell you, you'll never learn this reaction. But you don't need to learn the reaction to do this question. Right? For these kind of questions, I call it pattern finding. It's just like finding a pattern. Right? For example, I can tell you the sequence A, B, C, D. Something B, C, D, A, B, blah, blah. You know that it's A. Even if you don't learn A, B, C, D, you know that it's A. Right? So this is the same concept. I show you an example. You just have to apply this concept. Right? Or you can say find this pattern and find the pattern and select the correct choice. So this shows this reaction, and I ask you which of the following compound can be formed via this condensation from a single starting material. Right? In other words, I have this, afterwards I obtain these two. These two is this lah, but they are connected on the same chain. Right? So instead of them being separate, somewhere they are connected. So that you only have one single product. It makes sense, right? Which means that originally they are connected. After this reaction they are broken, but you still have one product. Correct? So now I'm asking you which of these can be formed, right? So if let's say I ask you which of it can be formed, the most commonsensical thing to do is to see which one can form this before they can break to form this. Right? Or you can work backwards also can. Right? So now if we look at if we observe this reaction first, right, we will realize something. The pattern is actually just break here, this will remain here, while this, the R prime O, will be connected here. Right? So now the fastest method to do this question is to find the R prime O. That's the fastest method. So now which one has the R prime O attached? It will be this, which can be a H3CO, or this, which can be this group here. It cannot be this because I'm asking for, because this must react with this, correct? For this is not possible because it's connected to the same one. So this is definitely out, this is also definitely out. No matter how complicated I draw, it's just to confuse you. Right? So if you can find the right method, this question can be done very, very fast. So now I'll cross out C and B. So it can only be A and D. Right? So which one is the correct answer? I'll first look at, if let's say I really form back this product, right? Does it make sense or not? Right? So what I do is I'll take these two ends, I'll join together and form back the product, and then I'll break them apart to see whether indeed I get this end and this end or not. Right? So now for A, how do I join them back? In other words, going from here to here. I have to break the R prime O bond, which is here. Right? Which means that for this I must break here. Right? Which means I must break here. correct? After I break here, where do I join it to? You see that for this, I actually join it to here, this end. So for here, I join to which carbon?
Is it this carbon?
Yes, precisely, correct? Which means this end should join to here, which makes sense. I never break any octet rule, correct? 1, 2, 3, 4, there's still 4 bonds, so it makes sense. So this we don't reject first. Next we look at this. Same thing, for this you cannot break this bond, correct? Because you need to separate this molecule, so it must be which bond has been broken? This bond. Correct? Huh? So this must join where?
This one
This carbon, the intersection. Can I join here?
cannot.
No, because I already break the octet rule. Which means that if let's say I really want to form this product from this, beforehand here should have 5 bonds, which is not possible. So the only answer can be A. That's the fastest method already. Right? Of course you can work out the rest out, but it's just to waste our time. Right? MCQ is about doing it with the fastest time. Right? So the answer is very obviously A. See, we never even write or draw anything. Right? So next is question 4. Right? This Pyritholone is actually adapted from Hwa Chong prelim, right? But I just modified it. So this is compound A and this, right? So which statement is correct? So first, both Pyritholone and compound A have 4 stereoisomers. Is it true or false? If it's false, then how many should it have? It shows A, right? Okay. So why do you think it's true? How do you make up the 4 stereoisomers? I believe you learned the 2 to the power of n method, right? So can you count for me? Where's the n?
This one, right? This one.
Can these have cis trans?
Cannot, right?
Why cannot?
This is like. Because this is cyclopentane.
Pentene,
Pentane.
right? Why?
Then it's like less than 7.
7, less than 8, right? So there's no way to twist it into a transform, so it can only be a cis form. So we don't count this since it's only cis, correct? So where else?
Can this double bond?
Can it? Can you have cis trans?
No, right? Cannot.
Why cannot? Using a double bond, shouldn't it form cis trans?
But this carbon has to like connect to 4, like 2 other.
So we are talking about cis trans here, right? So can you have cis trans? You say it must be connected to
2 other atoms, right?
2 other atoms. Then here, 1 here, 1 here, 1 here, 1 here. Why can't?
Because there's a C here.
So
there's a
what?
carbon here.
And then they are different. So if they are same, that means you can have cis trans, correct? But they are different. So why can't you have cis trans? So this is this part, right? So what do you see? What do you observe? Compared to a typical double bond. What's so different? representation, right, compared to a typical double bond, where are the atoms located at? Do they point in the same way as your typical double bond? This is your typical double bond, correct? This is your consecutive double bond, or we call it an allene system. So this is an allene, this is a double bond. For this, it can point in opposite directions, so we call this trans. For this, is there a way, can you say that, oh, these two point in opposite directions? Or these two point in the same direction? There's no way, correct? Because if you look from this angle, these two planes are actually intersected like this, alright? So allenes are not, we don't classify allenes as we don't use the term geometric isomerism for allenes, because there's no way to say that, oh, these two are pointing in the same direction or different direction. But allenes themselves are chiral, right? Why are they chiral? Because they have a non-superimposable mirror image. If you build another identical one, right, you will see that there's no way to, in other words, these two are not identical, although it might seem to some that it's identical, but it's not identical, right? I'll show you. So these two are mirror images, correct, of each other. Are they the same? Maybe you try flipping them to convince yourself. Can you ever transform this into this by rotation? No, you can't. So this is actually chiral. Allenes are chiral. There's no way to transform this to this. Of course, the criteria is that these two groups must be different, alright? Of course, if let's say you have a hydrogen here, then obviously you can transform one into another. And just plug out this, it's very easy to tell. Right? If let's say both are hydrogen, then of course they are identical. Right? So that means for this group, you have two isomers. For this, you have another isomer because it's chiral. There's 4 different groups connected to it. Correct? So 1, 2, 2 to the power of 2 is 4 for this. What about this?
This one is also.
Now I have 4 consecutive carbon, right? So what changes do you think you'll make? Observe this structure, right? And actually this is a true representation of the bonds, how the bonds is orientated, right? So if let's say I have now 4 carbon atoms, how do you think they'll be orientated? How will the other? Because when I have another carbon here, there will be 2 bonds, correct? One blue, one this. So how would they be pointing? Like that, or what?
It will be same as this, right?
Same as this, correct? Because it makes sense, right? The other bond must be here, and the other one must be connected here. In other words, now you have a geometric isomer once again.
This is trans.
Yes, correct. Because now you have a definition of pointing to the same side or different side, right? Why? Creative, not creative. Never think of it before.
Yeah.
Correct? So now, we look at allenes first. Actually, from allenes, we can learn a lot, right? So now, if you look at allene, now the question is, why is its structure like this, but not like this? Correct? So before that, we need to understand about hybridization state, right? What's the hybridization state of these 3 carbon? This carbon is?
The one sp2.
sp2, So the central one is?
sp.
And the last one is sp2 as well, correct?
Mm.
So now if you look at these 3 atoms, right, for this terminal carbon which is sp2, right, how is it shaped? You have a unhybridized, remove the C, you have an unhybridized p orbital, correct? This is your hybridized p orbital. I won't draw a small loop. There's another hybridized p orbital which is here, and there's another one here, hybridized p orbital with a small lobe. So one of these will form a bond with hydrogen, and another one will form with X, the blue atom, right? And another one will overlap with the hybridized p orbital of the central carbon. Right? Now, same thing for this central carbon, but this central carbon is sp hybridized. So since it's sp hybridized, you only have 2 hybridized orbitals, which is 180 degrees apart. Right? So for this, there's 2 unhybridized p orbitals. One is pointing towards this direction, and another one is orthogonal, which is at right angles. Right? So this will be responsible for forming a pi bond to this, which is this bond. Right? But for the other side, right, things is the same, just that it's rotated, whereby the hybridized p orbital will overlap with this to form a sigma bond, sigma sigma. And what happens is that the unhybridized p orbital is actually facing this way. If it's faced this way, there's no way to form a pi bond, correct? Which means that this pi bond now is formed this way. So now the other 2 unhybridized p orbital, one will be upwards, one will be downwards, to form hydrogen with to form bond with H and X, right? So that's why this bond is like that, while this pi bond is like that. So that's why the shape is like this, right? Now same thing, if you were to have 4 carbon atoms consecutively, this carbon will be sp2 hybridized, correct? If this sp2 hybridized, that means in order to form a pi bond with this atom, it must be this unhybridized p orbital. That means the other hybridized p orbital will form pi bond in this way, which is parallel to this, which means that these 2 bonds must be, these bonds must be on the same plane, right? Makes sense, right? So now, of course, no matter cis or trans or whether it's chiral or not, this is definitely contributes to 2 isomers, right? So you have one, I call it one center possible to exhibit isomerism. So this 1. Where else? This one cannot, right? Yeah, same thing. What about this? Something seems tricky here, right? So what about this part? Now let's say I change the question, if I simplify the question to like that, okay? X and something. Can I form cis trans for this structure? Because this part resembles this, correct? Of course, if let's say both sides are the same, I cannot have cis trans. That's why I place a double bond there, to tell you that the 2 sides are not the same. If the 2 sides are not the same, and I have a bond like this, definitely I can have cis trans, right? Because this side, the left side and right side is not the same. This side, the left side and right side is not the same. Even though it's sulfur, so what? Doesn't matter what. The key point is the restricted rotation about a particular bond. So I also can have cis trans here. Right? So this is the cis, because this and this is the major groups are on the same side. If I turn this the other side, it will be the trans. Right? This one got higher priority in cis trans allocation, right? So now this one cannot, because in a 4-member ring, there's no way to twist into a trans. So you will think that okay, 1 here, 1 here, so 2 to the power 2 should be 4. But the answer is wrong. Right? Your concept is wrong if you say that. This actually has 8 isomers. So where's the other 2? It has something got to do with the sulfur. Right? It's actually a trap there. I purposely lay out the trap. Right? So now what's the trap? Time for me to review. Next, okay, I draw this structure. So sulfur is from group 6, so you should have how many electrons? 6 electrons, valence electrons. So now there is 1, 2, 3, 4. So there must be a lone pair. Correct? So now, do you see 4 different groups connected to it? 1, 2, 3, 4. So what can I exhibit? Optical isomerism. Correct? Who says the other group cannot be lone pair? In fact, if you were to refer to isomerism behind there, there's actually a prelim question which tests on this. Right? The prelim question says this structure, right, R, can exhibit optical isomerism. They ask you to draw out and explain why. Same concept. Here's a double bond, here's a S, there's a lone pair, correct? So this lone pair is also a group. So in total you have 1, 2, 3, 4. Obviously, these 4 groups are different, so you can have optical isomerism. So same for this. So on top of this, cis trans, you can have a optical isomer here. So 2 to the power of 3 gives you 8. Right? Traps are everywhere, right? Usually I lay out a lot of traps, right? So the students can also learn a lot, right? Next, both these and these are not susceptible to attack electrophiles, right? So now you just recall what will attack electrophiles. Nucleophiles. Nucleophiles are electron rich, which means that if let's say there's nothing here which is electron rich, that means this statement will be false. So I just have to find whether there are places which are electron rich. Of course, I have double bonds which is electron rich, double bonds which is electron rich. There's lone pair on this oxygen which is also electron rich. Same thing for this, right? So this statement must be false. Next, both this has no geometric isomers, while this has 4 geometric isomers. Take note, just now I'm asking for stereo isomers, now I'm asking for geometric isomers. This will test whether you can differentiate between these two, right? So geometric isomers means cis trans, right? For this, there's no geometric isomers. For this, it's not a geometric isomer, by the way. It is chiral, right? But for this, yes, it has geometric isomerism, right? So you have one here, another one here, remember? So 2 to the power of 2 is 4. So C must be true. Lastly, this has 4 adjacent atoms, they are sp2 hybridized, while this has 8 adjacent atoms. So for this, you will count 1, 2, 3, 4. These 4 are all sp2 hybridized. Right? Or for this, 1, 2, 3, 4. Those people who never spot the lone pair will count these as 6, 7, 8. Right? But take note that this sulfur has a lone pair, like what I mentioned. So when there are 4 different groups, what shape will it adopt? You adopt the trigonal pyramidal. And you know for sp2 it is planar. Correct? So this is not sp2. So in fact you only have 1, 2, 3, 4, 5. Right? So traps are everywhere. Take note. So the answer for this is C. Right? Lastly, last MCQ, which of following species is the worst nucleophile? Actually, this is a simple question, just that I want to complicate your choice, right? So the first thing you ask yourself is, what is a nucleophile? Nucleophile is electron rich, right? So now, can you tell me what are the net charges of these species? The first one is -1, this is 0, 0, this is +1. So obviously, which one cannot be a nucleophile? The last one. I don't even have to work out and draw the dot and cross whatsoever, right? Neutral species, of course, you can be nucleophiles. For example, H2O, there's a lone pair there, you can add a nucleophile, right? But for last species, no, it's positive. So D must be the worst nucleophile, right? So this actually can be done very fast. Same thing as this and this. These 3 questions are quite straightforward. Just that these and these will require a bit of time, right? Now the last question is the basketin. It's not a molecule which I made up, it's a legit molecule, right? So this is the structure of basketin. So after some radical reaction, it becomes basketanol. This one is the one that made up, right? So what is the equation for the combustion of basketanol? This one should be quite straightforward, right? You just have to count the number of carbon, oxygen, etc. Right? So what is the formula of basketanol? Oh, you managed to draw it, right?
But I don't know whether it's correct. So
Is it correct? What did I say here? To give or what?
tertiary.
Is this tertiary alcohol? This is testing you on the concept of degree of substitution, right? Which is this degree of substitution thing was added in this year to a new syllabus. Last year, right? So what is a tertiary alcohol?
Not sure.
See, if let's say I have these 3 formulas, right? This kind of alcohol is known as a primary alcohol. This is a secondary. This is a tertiary, right? How do I tell? I just have to ask myself, how many carbons are attached to this carbon? If there's 1, it will be primary. 2, secondary. 3, tertiary. You cannot have 4, right? So this is primary, secondary, tertiary. Of course, you can have, apart from alcohols, you can have other functional groups. So for example, amines. You can have a primary amine. Sorry, amines doesn't work this way. amine is like that. This is a primary amine. This is a secondary amine. This is a tertiary amine. And you can have a quaternary amine, right? Which have 4 groups, but you must adopt a positive charge, right? So these are just classifications. Of course, you must know what is a tertiary alcohol before I do this question, right? So now, since I already told you what is a tertiary alcohol, can you draw me the structure of the tertiary alcohol? I'll pass it to more. It's just like a box which is open, correct? Can it be on the lid? Cannot be. It will be secondary. So how do you get a tertiary alcohol?
Over here.
Only there? Are there any other places which are possible?
Here also.
Can, but does it matter or not to the formula? So it doesn't matter, correct? And I just asked for the equation, so it doesn't really matter, right? Even if you draw here, it doesn't affect the formula, right? So this is actually just a giveaway. So write the equation first. Build it. Am I too fast or okay?
Okay.
Okay. Balance it, huh? PC10H?
H11.
11. Okay, correct. Is it balanced? Balanced, Alright, to state the type of reaction that plus ketane has undergone. Of course, not radical reaction, right? Otherwise, why do I ask? So what type of reaction? It's not a free radical substitution. How do you know? I also never show you the mechanism. When I tell you radical reaction is not, it might not be a free radical substitution. How you know it can be a free radical addition also, right? So the safe method is, for example, I have an alkane, right? If I change it to an alcohol, what type of reaction is this? Remember what we talked about just now? Finding the oxygen state? But this is very obviously everything should be 0 lah, if we don't consider hydrogen's electronegativity. What about this? It will be, this is -1, right? Here should be +1. So from 0 to +1 it is an oxidation. So this is actually an oxidation reaction, right? So the type of reaction is just oxidation, right? if only I show you, for example, very clearly that this plus bromine 2 UV give you this, and I ask you what type of reaction, you will know that it's free radical substitution, because the key criteria is you need UV, right? For this I never draw anything, so you cannot say it's free radical sub. Right, next, it was found that the Baskin-Ternov form does not rotate plane pairwise-like. So what are the possible structures? I've built the basketing, right? So in order to obtain a tertiary alcohol, right, the alcohol, must it go here only? Can it be here? Cannot be here. It can be here, correct? Can it be here? 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 This side is the same, because it's symmetrical, right? So if let's say the alcohol attaches itself here, does it rotate plane pairwise like this molecule? How do you tell? It's supposed to be straight on. Let's say I give you a random molecule and then ask you, does this rotate plane pairwise like? How do you determine?
Whether it has a chiral center, then non-superimposable images.
Okay, so does it have? Hard, right? Hard to tell. So in fact, a lot of students define chirality as what you have just said, correct? But the easiest way to tell whether a molecule is chiral or not is just to find whether there are any mirror planes, right? So for example, is there a mirror? Do you know what's a mirror plane? You know, right? If let's say I ask you, if you ignore the words here, right? Does my phone have a mirror plane? Yes. Here. Left and right will reflect. Remember, in primary school you did questions like, they give you this side of the figure and then they draw dotted line. They ask you to finish the figure, correct? It's the same idea. Just that now, things become 3D. So for example, like this case, originally this case, does it have a mirror plane? Yes, there's two, one here, one here. The left and right side is the same, right? Now if I attach it here, does it have a mirror plane? Left and right is not the same. Left and right is not the same, so there's no mirror plane. If there is no mirror plane, it is definitely chiral. In fact, the definition of chirality, if you refer to my isomerism note, you'll see that I do not define it as carbon bonded to four other things, etc. Right? As long as there's no mirror image, it will be chiral. That's the definition. That's a straight definition. All the other small definitions like carbon whatsoever is based on that definition. So if that definition on top can go wrong, the bottom one cannot go wrong. Right? So this is definitely chiral, right? But I'm asking for the ones which are achiral because they do not rotate plane pairwise like. So it means this already cannot be here. Can it be here?
Cannot.
Because here and here is the same. Correct? What about here? Does it have a
it's
mirror plane?
chiral, right?
Is it chiral? Is this molecule chiral?
Just here, the mirror plane.
You will think that, okay, the hydrogen is pointing here, right? Correct. It doesn't look as if it's chiral, but take note that sigma bonds can rotate. This is not pi bond whatsoever, so it can actually rotate. Correct? So as long as one of its configuration gives a mirror image, it won't be chiral. So this won't be chiral because there's a mirror plane here. Correct? So this is one of the answer. And of course, I think you should have thought about it already. The which can also be here, which makes this a chiral as well because there's a mirror plane here. So in fact you have two answers. One here, one here. We don't talk about the other side because it's the same. Right? So there's only two answers, which is one here, one here. Right? So there are two molecules. You just have to draw these two can already. Right? So you can draw it now. Well, how do you get this? Who's get? A star.
I went to some it was like
Organized by A star.
no, it was organized by NUS High.
Oh.
Then we went to A star.
Do experiments whatsoever, is it? Oh. I think they have it annually or something.
Yeah.
So if you go back and see my isomerism notes, actually all of these are already talked about already, right? Yes, correct. Okay. So for the next parts, you will use the structure of Baskin-Ball that you propose here, right? So you have predicted that any one hydrogen atom in Baskin-Ball can be replaced by the isotope deuterium, which is D. And Baskin-Ball's chemical properties will still be retained, right? Because isotopes aren't supposed to have different chemical properties, right? So now draw the isomers of the deuterated compound. They are achiral. So now you can choose any one, right? Which one you want? Because the answer will be the same. I'll tell you first. So let's say we start with this one, right? So you know that there's hydrogen connected here, 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 all the way until here also, correct? So you can replace any one of these with a deuterium. So I replace deuterium with a blue one. So I'm asking you, how many of these deuterated compounds are chiral? Are chiral or achiral, right? So first we talk about this. Is this chiral or achiral? It's achiral. Okay, achiral, good. So where else can I sub? I can substitute here, correct? Is it chiral or achiral? Does it have a mirror plane? If let's have a blue one connected here. I don't have a mirror plane. So this is chiral. Do you know how many chiral we talked about already? Sorry, achiral. We already have one achiral. This is chiral. Correct? Now, what if I put it here? You still
chiral.
Still chiral. If I put it here?
Achiral.
Because it's a mirror plane. Correct? Huh? So do I talk about this side? Do you think this side is the same or different?
It's the same.
You sure? Just now when we talk about same or different, we are shifting this group, correct? Left and right. But do you think placing it here and here give you the same compound or different compound? Placing it here and here. You get the question, right? Do you think placing? You sure? Placing here? Chemical properties wise, yes, the same, but structure wise, it's different one. There's no way to rotate this into this. Correct? So these two are actually different. So just now you have 1, 2, which is at here, and another one is 3, because there's a mirror plane one. The mirror plane still exists, 3. And the next one, which is here, 4, because there's still a mirror plane. Right? Correct? Huh? What about here? Is it chiral or achiral?
Chiral.
You sure? Remember, even though I never plug in all the hydrogens are still there. Correct? Is this chiral or achiral? The left side and right side, is it the same? It's not the same. Correct? Because remember, when we talk about rotation, about sigma bond, we are talking about like that. We are not talking about like that. Okay? This is not rotation already. This, in order to do it this way, you must break the bond. Right? Rotation is not about breaking up the bond. So this is actually chiral, because left and right is not the same. Or some people call it, okay, carbon bonded to 4 different groups also can. Right? Depending on which one you want to adopt. Same thing for this one, I don't have to show because it's the same. Right? So in fact you have 1, 2, 3, 4 isomers which are achiral. Right? Are these questions hard? Or must visualize?
Like, need to visualize.
Yeah, that's why, right? Isomerism is about visualization sometimes. So draw the isomers that are achiral. There should be 4, right? Nowadays the deuterium, that kind of questions is very popular.
other guy that is in your class is from which school?
RJ.
Oh.
Yeah, right. Okay. Next. Hence or otherwise state the total number of isomers and stereoisomers possible for a deuterated compound. So now you must consider everything, right? So now you can do it systematically. Once again, just now we already counted 1. We start from here, so it can be here 1, right? 2, 2. No need to draw, just state can already. So we have 1, 2. What about here? Do I count here? You sure?
Oh wait.
Is this chiral or not? If let's say I put it here. It's chiral, correct? Now imagine I have its mirror image reflected here. Right? Which means the other one must be connected here. Which is like that one, connected here. Make sense, right? Which means I don't have to plug in here and count it again. So there will be 1, 2, 3, which is the mirror image. 4, I don't count this. Okay, so 1, 2, 3, 4. Next, this side. Next. So these two is settled, this side, 4. Next, same thing. 5, 6, because these two are achiral. Okay? Same thing for this. 7, 8. Same idea as just now. 7, 8 already. What about here? We have 9. We have 9. These two can swap sides because it's chiral. 10. Same thing for this. 11, 12. So total we have 12. Right? This one you can visualize. If you want to borrow back also can, right? So the last part is drawing of mechanism. So from this point onwards, you can abbreviate basketanol as R3COH, right? So just C R OH, right? So I don't have to draw this repeatedly. So basketanol can generate an ether product in H2SO4. So for this, I'm testing you on whether you know what's an ether. Right? An ether is a group has this formula ROR. Correct? So this is an ether. So in H2SO4, and the reaction mechanism is thought to proceed via the following stepwise mechanism. And this type of question is also very popular nowadays. They give you the step-by-step mechanism, and this mechanism usually you will never learn it before. So it's basically just following the recipe and coming up with the mechanism. So next, basketanol can undergoes an acid-base reaction with H2SO4. How do you illustrate that? This is an acid-base reaction, correct? So now you have a R3COH reacting with H2SO4. If let's say I tell you it's an acid-base reaction, what should be the product? Definitely HSO4 minus must be one of the product. Then the other one, it becomes R3COH2 plus. Okay, okay, this one. Next one, a CO bond is broken heterolytically, right? So the keyword is heterolytically. So if you want to draw these species, also can. OH plus. So if you want to draw this product, it's actually like that, this structure. So now a CO bond is broken heterolytically, so very obviously it's this bond. So if let's say I break this bond heterolytically, does it go to the O or does it go to the C? You should go to the more electronegative atom, which is O. Also explained in my notes. So once this leaves, you will have a positive charge on this carbon, which is a carbocation ion plus H2O. Right? Conservation of charge before and after. So next, a new CO bond is formed. Remember, you must generate this ether product. So how do you form a new CO bond? You cannot be this O attack here, otherwise you will form back your alcohol, correct? So since you must have this, and in order to have this, there's only one possibility, which means that another Basketanol must attack here. OH, right? So this is the only possibility. Don't worry, I won't give you options which there's a choice one, right? Otherwise it will be too difficult. This is the most difficult than anything else, right? So to form a new CO bond, so once I have the new CO bond, right? Remember, I don't just break off the CH bond. Whatever that's attached is still attached. But now I have a positive charge on this O. Same thing, conservation of charge. Before, after. And the last step is a deprotonation. Remember, I must obtain my ether product, which is this. And in order to obtain my ether product, I'm only one step away. I have an ROR. I just have to remove this thing, right? So in order to deprotonate it, I can just use a base or use my HSO4 minus because it's a catalyst, right? So I can either draw it this way to deprotonate it, or I can draw HSO4 minus, deprotonate it. So now I'll have my this product line, RRR, and regenerate my H2SO4. Right? Each of these following the step of this, right? So it's okay if you don't copy because this will be given to you anyways, right? So this is finished. So how do you find this? Difficult?
Yeah, difficult. Like,
But it's open book, so it's supposed to help you.
yeah.
Okay. Do you have any questions? Which part you are still confused?
Not really. But I can understand.
Good. Okay. Forgot to ask you. Do you have any questions from your school or what? Wait, your holidays now, right? When does the school start?
Next week.
Not tomorrow. No, not 2 days later, right?
No.
It's the second week, right?
Yeah.
Oh, okay. Okay, so for now, since you don't have anything yet, you can go through time bonding first to revise a bit, right? But before that, you can go through the true-false questions. Just take about 2 to 3 minutes. If you are unsure, you can just leave blank. worry, right? I won't tell the answer until you've gone through, right? That's okay, not a lot wrong, right? So go through with you. So some basics. Atoms tend to attain octet or duplet configuration to achieve maximum stability, right? Duplet is for hydrogen, octet is for the rest. And notice I write tend to, I didn't say must, right? Because there are exceptions, such as radicals, those which can have more than 8 electrons and those which can have less than 8 electrons, right? So they do this by losing, gaining, or sharing electrons. You learn this in your O levels. So the tendency for an atom to lose or gain or share electrons can be predicted using electronegativity, right? So here is the electronegativity table. You don't have to memorize the table, but you have to know how the trend is, right? So electronegativity is the ability of an atom to attract electrons towards itself. High electronegative means, does it donate electrons readily or does it accept electrons readily? Accept, yes, right? So the other one is donate, which means which atom will donate electrons most easily? Francium, right? Which means that francium is a what agent? It's a strong one.
Reducing.
Yes, so it's a strong reducing agent, correct? So which one is the strongest oxidizing agent?
This one?
There's a trap, huh? Can you tell easily or not? You can't, right? If everything can be told so easily, then why do you need this? Correct? So in fact, if you want to compare those from the same group, yes, you can use electronegativity maybe to explain. For example, if you compare francium and lithium. So that's why you can put lithium in water, you won't die, but if you put francium in water, you'll die because you'll explode, since it's a strong reducing agent, right? So this electronegativity explains it. In fact, you can see that much of chemical bonding revolves around electronegativity, right? So across period, why does across period electronegativity increase? Is due to the increase in effective nuclear charge, right? You know this equation, right? Effective nuclear charge, which is Z equal to Z effective equal to Z minus shielding effect, correct? So across the period, this increase while this remains relatively constant. This is your atomic structure, right? So therefore Z effective increases across period, which means that electrons are more tightly bound, which means that across period your radius will be smaller, right? And this is also a reason why electronegativity increase, because across period Z effective increase, you can pull electrons more strongly to yourself, so electronegativity increases, right? So for down the period, down the group, same thing. Z increase, right? But shielding effect increase at a much faster rate, which means that Z effective actually decreases. So if Z effective decreases, that means your electronegativity will decrease down the group. That's the trend, right? So now, therefore, what is expected to have the highest electronegativity? It will be fluorine, while francium is the lowest, right? So now, by deduction, elements diagonally related have similar electronegativity. Hence the term diagonal relationship. I believe is your school notes, right? This part, at the behind part, should be in the appendix, usually. And people usually, I know students usually just all the challenging questions, not compulsory one, just flip, correct? So now, by deduction, elements diagonally related have similar electronegativity. Hence the term diagonal relationship is used to describe them. Right. So now, why are elements that are diagonally related have similar electronegativity? If you refer to this, you can see for example, lithium and magnesium, beryllium and aluminium, boron and silicon. They have very, very close electronegativity, right? Now you see, if let's say I have this periodic table, right? So like what we mentioned, Z effective increases this way and increases this way. So it makes sense to think that these two have the same electronegativity. Correct, right? If let's say here is 3, 4, 5, here is 4, 3, these two must be the same. Correct? But is it right to say that these two are the same? These two are the same? These two are not the same. Take note, these two are not the same. Only those that are diagonally related like these are the same. So I believe that can solve some of your true-false questions, right? So, as chemical reactions involve electron interactions, elements that are diagonally related have similar chemical properties, right? I'm not saying die they must have, just that they tend to have similar chemical properties, right? So here's an example: lithium, magnesium, beryllium, aluminium, boron, and silicon, right? So here's an example: lithium is the only group 1 metal that forms stable nitride, which is similar to all the group 2 metals, right? Because they share similar electronegativity, and usually is for the elements which are above here. Those that are below here don't really have that much of diagonal relationship, right? So this is for diagonal relationship. Next, electronegativity difference. The first concept is electronegativity. This is the next concept, right, which is important for bonding. So in fact, this chapter is split into fundamentals, followed by intramolecular bonding, such as ionic covalent, followed by intermolecular forces, followed by your solid state structure, right? So in order to predict the type of bonds, you have to understand the relative electronegativity values. The best is to memorize a few of them, right? So for example, the most common ones, I would say that the first 2 or 3 periods are the most common ones, right? So first, non-polar bonds. Non-polar bonds are usually formed between elements with electronegativity difference of less than 0.4. So for example, between carbon and hydrogen, their electronegativity difference is about 0.4, right, which is non-polar, we call it. So if the electronegativity difference is low, you can see that the bonding electrons between two are more or less shared equally. None of which will have more, none of which will have less, right? So it's shared equally, so we call it a non-polar covalent bond. And it's usually formed between non-metals, right? It can also form between metals, which we call it metallic bond, right? Because for metallic bond, of course, there's electronegativity difference is 0, right? Same thing for next is for polar bonds. For polar bonds, their difference is between 0.4 and 1.8. So for example, oxygen, hydrogen, their difference is 1.4. So it's a polar bond. Between fluorine and hydrogen, it is 1.8, which is also a polar bond, right? So these kind of scenarios, if the electronegativity difference increase, if let's say X is more electronegative than Y, what will happen is the two bonding electrons will be closer to X. See the difference, So once it's closer to X, there will be more electrons around X, so that they will have a partial negative charge compared to a full negative charge, which is like that. This one means that the two electrons totally go to X already, but this means that, okay, it's close to X, but it's not really totally on X, so that's why we assign partial negative. And of course, the other one will be partial positive, conservation of charge. And we will draw this arrow pointing from the positive end to the negative end. So this is known as a dipole moment, right? Right. So the dipole moment pointing from the less to a more electronegative atom, or from this charge to this charge, right? So now, here are 3 examples. So what differences do you see? So I think the hint is quite obvious, right? And can you explain why it's like that? What difference do you see?
Like,
The first difference.
first one, the electrons are more closer to F
Then to O, then to N. Why?
the difference in electronegativity between F and H
Is
O
greater.
and H, yeah.
Or the keyword is just F has a greater electronegativity than O, than N, right? So that's the first thing that you see. First difference. What's the second difference?
The dipole moment.
It's longer because the bond is more and more polar, right? So you can write down notes, right? I'm fine with anything. You don't have to fill in. Right? There's a second difference. What's the third difference?
partial charge.
Yeah, which one is greater? This one is greater. Right? Why is it greater? Let's talk about negative lah. Why is the negative greater for this?
Because the electrons are closer.
Yes, correct. Because the more close it is, the more it will resemble a full positive charge, right? So that's why I draw it like that, right? Right, next, ionic bond. So for those with electronegativity difference greater than 1.8, one atom will absorb, right, sorry, not absorb, will attract the electron, the bonding electron towards itself so much that these two electrons virtually lie on one atom only, while stripping the other one of its electron. So for example, you have NaCl, the difference is 2.1. Don't talk about NaF lah, right? It's even more ionic, right? So this is how you form ionic bonds. So in summary, you see that as long as my electronegativity difference is 0, it's nonpolar. As it increases, it becomes more and more polar and eventually ionic, right? Of course, this 1.8 whatsoever is just a rough guideline. Some people prefer it to be at 2, some people call it, say it's 1.6, doesn't really matter, right? It's just relative. So this is just for information, a Van Arco triangle. This Van Arco triangle is plotted difference in electronegativity against average electronegativity, right? And I won't go through this in detail. You will see from your practice, right, how to apply this. So next is your oxygen state, learn by example. So electronegativity is essential to work out the oxygen state. I already told you the minus plus method, so I just repeat again, right? So for example, I'll start off with this, right? You have nitrogen and oxygen. Which one is more electronegative? Oxygen. So it will be minus minus plus plus. The other one will be nitrogen and carbon. So nitrogen is more electronegative. So it will be minus plus. Take note, nitrogen got 2 lone pairs. We don't count the 2 lone pairs because it's not bonded to anything, right? So in fact, this oxygen state will be plus 1. Right? Now, what about carbon monoxide? Some students say, if I use the minus plus method, since there are 3 bonds, shouldn't I obtain this? Then shouldn't O be minus 3, then carbon is plus 3? Right? But obviously, oxygen is minus 2, carbon is plus 2. But why is this wrong? If you were to look at carbon monoxide dot and cross diagram, you realize something strange about it, right? If you haven't realized it. Carbon, the dot and cross diagram is actually like that. Right? Dative bond, right? So in fact, the correct structure should be like that. So if you were to look at the bonding in this way and work out the oxygen state, then yeah, it's correct. This bond doesn't contribute to anything because both are from oxygen, right? So I won't work out the other examples. The other examples you can try out since I already gone through this, right? Go to the next part. So next, intramolecular bonding. We'll talk about ionic bonding first. So formation. I believe this, all those people who do H2 chem should memorize these already, right, by heart from O levels, right? So strong electrostatic forces of attraction between cations and anions, right? The keyword is strong electrostatic forces, right? That's the keyword. Later on, you'll see why I want you to think of these 3 words, right? So next, structures. Ionic bonds are non-directional, right? Non-directional. Do you take physics? You take bio? So you know forces, attractive forces they don't have a direction, correct? If let's say the earth is here, the satellite is here, you attract. Even if it's here, you attract. Here, everywhere you attract. That's what is meant by non-directional. Some forces which are directional is tension, depending on where the rope is. If let's say a rope here and you are standing here, there's no tension, correct? So they are non-directional. Ions are held in fixed positions in an orderly arrangement by strong ionic bonds forming an ionic lattice, which we'll discuss later under solid state. So strength-wise, right? Strength depends on lattice energy, right? Which is due to electrostatic attractions between opposite charged ions. So can you still remember the lattice energy equation?
The product over sum, right?
Yes.
Product of,
Remember the modulus,
yeah.
Mm.
But like I forget like how to repeat.
Q plus
Ah.
times Q minus divided by R plus R minus, mod the whole thing, right? So as long as you understand this formula, you can compare their relative melting points, boiling points, ionic strength, etc. Right? So I'll say that this equation is quite useful, right? So not all lattice energy are as predicted due to covalent character present in ionic bonding, which we'll discuss later. So here's the dot and cross. This one I need not go through. Next, metallic bonding. Look at the three keywords. Strong electrostatic forces, right? So this is also electrostatic in nature between lattice of metal cations and sea of delocalized electrons in giant metal lattice. So alloys also have this structure. So metallic bonds are also non-directional because it's the attraction between electrons and the cation, which can be anywhere on the electron, right? So it's also non-directional, and the layers can slide across one another in giant metallic lattice, right? So strength-wise, it depends on charge density, which is proportional to the number of delocalized electrons over cation size, right? I've already written the formula, so it's actually just proportional to Q over R, which is your charge density, right? So now, why is it proportional to this? You can think of it this way. If let's say you compare metallic bond with charges plus, another one is plus 2, plus 2, plus 2, which one will be stronger? It will be this one. Because for this, every metal contribute 1 electron. This has double the electron, it has double the charge. So it makes sense to think that the attraction is stronger. But what about radius? Why is it smaller radius, stronger metallic bond strength? If you compare this with another one with smaller ions, right? These ions, these charges are concentrated in a smaller volume compared to this, which are more dispersed. So the attraction between this and the electron is ought to be smaller, right? Now imagine if let's say I have a surface area, if I calculate the charge divided by the surface area, each of these small surface area will receive very, very small amounts of charge, while for this is much greater charge. So this attraction is going to be stronger. So that's why it's Q over R, right? Next, for covalent bonding, this part is what JC chemical bonding revolves around, right? Majority is about this. So formation, same thing, strong electrostatic force, right? So now, if you were to compare this, all of them are strong electrostatic forces of attraction. So can you say covalent bond is the weakest? No, you can't compare them because all of them are electrostatic forces and all of them are strong, right? A lot of people tell me covalent bond is the weakest. That's why your water can evaporate and will boil at 100 degrees Celsius. But for that, you are actually not comparing intramolecular bonding. You are comparing intermolecular forces, right? These two are different. So atoms achieve octet configuration by sharing electrons. So usually formed between two non-metallic elements which have small electronegativity difference, like what I mentioned just now, non-polar or polar, right? And notice, I say usually formed between two non-metals, but it can be formed between metal and non-metal as well, because what matters is the electronegativity difference, right? So if you refer to this compound, right, you can see that Mg is a metal, right, but it can still covalently bond to carbon and bromine. Why? Because of the electronegativity difference. Carbon minus this is about 1.3, so it's a polar bond. Bromine 2.8 minus 1.2 is about 1.6, so it's also a polar bond, so it's not an ionic bond, right? So what matters is the electronegativity difference, not the metal or non-metal, right? So structure of bonds, sigma and pi bonds, they are formed when orbitals of two adjacent atoms overlap to share their electrons. there are two kinds of bonds formed by two distinctive types of overlap. Of course, there are other types, which you will see in the practice, right? Make you draw other types. So for the sigma bond, the type will be known as a head-on overlap, right? This one I've learned, so you can fill in the blank. Or the other one will be, yes, side-on or sideways, right? Sideways overlap. So these involve SS, SP, PP. Actually, this doesn't matter because the true definition of sigma bond is just head-on. So no matter you have S, P, D, or even F, as long as it's head-on, it's a sigma bond. You don't really have to care. So the concept is about head-on. Same thing for pi bond. The concept is about sideways. It's not about what orbitals are involved, right? So electron density, this is concentrated between a nuclei since it's head-on, and this is above and below the bonding axis. This is the bonding axis. So it can, some people will tell me, okay, it must be one electron here, one electron here. But no, both can be here, or one here, doesn't matter. You can't control electrons, right? So in fact, we will say that electrons are distributed both here and here, above and below the plane, right? So now, for sigma bonds, just now I already mentioned, you can rotate sigma bonds, correct? So rotation for this is allowed. But for pi bonds, can you rotate about a pi bond? No, you can't, right? Because pi bond is rigid. Like this, you have a pi bond, there's no way to rotate. Unlike a sigma bond, which you can rotate freely, right? So orbital, this is effective due to a larger extent of overlap, while this is sideways, because it's less effective, because the area of overlap is smaller than this, right? It's just like two collisions between collision between two cars, right? This is greater in strength and this is weaker in strength, right? Would you prefer a car bang you on the side or in the front? Of course, at the side, it's less severe, right? Same idea. Which means that the strength of this is greater and the strength of this is weaker as well. So usually a pi bond, not usually. If let's say I have a pi bond and sigma bond, the pi bond must break first before sigma bond because pi bond is weaker, right? So in covalent molecules, there must always be one and only one sigma bond. You cannot have two. Single bonds are made of one sigma bond. Double bonds are made of one sigma, one pi, while triple bonds made of one sigma and two pi. Right? Later on, you'll see. In fact, if you were to look at this cover, usually I put something interesting in a cover. So, for example, how many bonds are there? 5 bonds, right? So, how many sigma bonds are there?
5 sigma.
Sigma bonds there.
Oh. 1.
Yes, correct. We just learned. You can only have one sigma bond. There's no way to overlap twice one. So, in fact, I can just set this as a question and ask you how many sigma bonds are there? A1, B2, etc. Right? I believe a lot of people get it wrong. Doesn't matter, right? Even I draw 1000 bonds, it's still one sigma bond. Right? So that's the interesting thing about understanding of concept, right? So example 2. How many sigma and pi bonds can be found in this molecule? Pi bond first,
Pi bonds first.
Yeah, how many pi bonds are there? Because pi bond is more tricky. 3, is it? By the way, you can forget about the benzene part because I assume you haven't go do benzene yet, right? Because it's just bonding. So 3, is it? Where's the other one?
Here.
Good, right? So sometimes examiners can be nasty, they don't draw it out. So for example, COOH, right? It's just like that, put like that. But there's a hidden double bond there, right? So just be careful. So in total there's 4. So how many sigma bonds? 1, 2, 3. You just have to draw the whole structure and see how many lines can you draw. So 1, 2, 3, 4, 5, 6. Don't forget here 7, 8, 9, 10. A lot of people forget the hydrogen. 11, 12, 13, 14, 15, 16, 17, 18, 19. Right? So next, coordinate dative bond. Formed when orbital containing a pair of electrons what overlap with ignore this part first. Formed when orbital containing a pair of electrons overlap with the empty orbital of another atom. Right? You have learned acid base. Correct? So what do you call this kind of species? They contain electron and they donate the electron to another species. So electron donors are, in other words, electron donors and electron acceptors. So electron donors are known as what? You learn this. What acid? Lewis. Electron donor is what? Lewis acid, you sure? Or is it Lewis base? Lewis what?
Lewis base.
Yes, okay. Electron donor is a Lewis base. Electron acceptor is a Lewis acid. So the two blanks are for you to fill in. Right? So don't be confused if instead of using electron donor, electron acceptor, they use Lewis acid, Lewis base. Right? In fact, these two added in the new syllabus. Right? Last time no. Last time just bond state enough really. Right? So that's why I included here as well. So dative bonds have similar properties as normal kind of covalent bonds. They are not any stronger or any weaker. They are the same. And most of the time they represent it with this. It can be represented by this, but most of the time it's drawn in a normal covalent bond fashion. So for example, right, I believe this example many schools will give. It's a standard kind of example. Right? This kind of. Usually, what they'll do is they don't draw this bond this way, but just draw it this way. Okay? So you have to know which bonds are the covalent bond and which bonds are dative bonds. Right? So next, try this example. Al3Cl8. Of course, I won't ask Al2Cl6, right? That one is too common already. You're almost there. So first I have 3 Al Cl. I just use X on X. So instead of working on the dative bond first, I work on the normal bonds first, because this is most likely I won't say dimerized, a trimerized product, right? So originally, each aluminium should be joined to 3. So 1, 2, 3, 4, 5, 6, 7, 8. Right? But if let's say this is really a trimerized product, AlCl3 will give me Al3Cl9. Correct? But this is Al3Cl8. So 1, 2, 3, 4, 5, 6, 7, 8. This is the only possibility. Correct? So in order to balance it, I just have to draw the lone pair like that. This is like that. Correct? How about here? Just like that lah. Why cannot? Cannot. Right? And of course there are other ways to draw it. So instead of drawing the dative bond from these two, I can draw it like that. And this come like that also can. Right, so this shows, and in fact dative bond is the same as a normal covalent bond, so no matter how you draw, their chemical properties remains the same. Right, so there are many ways to draw it. Yeah, like that also can, right? So will this structure be favored at high temperature or low temperature? Of course, compared to AlCl3 lah, right? So will it be more favorable at high temperature or low temperature compared to AlCl3? You got a question, right? You understand the question, right?
Yeah.
Okay. In other words, this to this, is it favorable at high temperature or low temperature?
High.
Why? Is it because at higher temperature you have more energy, so you can break the bonds to form AlCl3?
Yeah, that's what I was thinking.
Okay, good. Correct.
Oh.
Let's say out, right? That's one correct answer. Of course, there's another answer. This answer revolves around energetics, right? So now, from here to here, delta H is positive or negative? Bonds are being broken, right? So delta H is it positive or negative if you break bonds? Positive, right?
Positive.
You need energy. So what about delta S? Is it positive or negative?
Positive.
It should be positive because you have more of this, right? So now delta G is equal to, you learn energetics already, right? Minus T delta S. If this is positive, this is positive, right? At what temperature will this be favorable? High or low?
Higher temperature.
High, correct? That's another way you can explain it in terms of energetics, right? There are two ways. So what about this one? Be2Cl4 dot H2O2.
What to do when there's a dot?
Dot. So I can just treat it as X2 lor. Right? Just put a dot there to separate the two. Or you can call it the water of crystallization. Right? Remember, you must achieve octet. Just for information, if you don't know this, AlCl3 can polymerize, right? Like what I showed you just now. It can form a very, very long chain. Same thing for BeCl2. BeCl2 can also polymerize, right? BeCl2 adopts this structure. BeCl, Cl, Be, and so on. Right, Cl, Cl, and so on. So what they can do is that there's the lone pair here, correct? You can donate to here. DCl can donate to here. DCl can donate to here, donate to here, and so on to form a polymerized chain. Right? So these two general structures you have to know. So you can just work on this structure, right? So BeCl2, Be2Cl4 is just this part of the structure. And remember, I have two H2O, correct? So what does the H2O do? Remember, oxygen got lone pair. So you can donate to this B, or the other oxygen donate to this B. So everything achieves octet configuration. So it's stable. Right, so this is how you draw your Be2Cl4H2. Yeah, okay. And of course, if let's say you react BeCl2 with Lewis base, that's you, Lewis base, right? That's Lewis base. So Lewis base is a what? Electron donor, correct? Okay, good. So in fact, I can say BeCl2 reacts with my ammonia, and if let's say BeCl2 reacts with ammonia twice, I'll get this structure: ClCl, ammonia, ammonia. Right, where everything achieves octet. So there can be a lot of funny patterns that can come out from these kind of questions, right? Okay, so we can